Great. I'm Jeff Lynn. Katie is going to be a tough act to follow. I want to acknowledge Larry Santucci, who did a ton of work in organizing this. What's been a fantastic event so far. It's really exceeded or met my very high expectations. And also Nicole and the rest of the conference team here, who are, uniformly wonderful in all of my experience with them. This is a project that is joint work with Dan Moulton, Isaac Rand, and Robin Smith. There's Robin. Hi. And they really deserve a ton of the credit here. This has been a real team effort. I've just listening to Katie's talk. This is actually the first co-authored project where I'm the first alphabetical. This has never happened in my career. Okay. The usual disclaimer applies here. Okay. So what are we doing here? We're going to be digitizing the Census of Housing block statistics. What are the Census of Housing block statistics? So in 1940, the Census Bureau decided for the first time to start releasing these small area public use estimates at the level of blocks. These are statistics about housing. And before 1970, these statistics mostly exist only in the form of printed or scanned tables and maps. And so this is a rough estimate, but there's at least like tens of thousands of pages of these tables and maps showing us where the geometries of the blocks exist in geographic space. Okay. So what is in them? So I'm going to talk on this slide about what's in them, and then give you some ideas of like what are some use cases that I think are potentially pretty exciting with these data. So these the block statistics measure characteristics about tenure, so home ownership or renters, occupancy, so occupied units versus vacant units, structure age, structure condition, rents and values, and race of occupants. Okay. Importantly, I think one feature here is that we are recording in the housing statistics the characteristics of not just occupied units, like in the population census, but also for vacant units. And that's important, especially important in this era in the middle 20th century, where, especially in central cities, housing abandonment, housing maintenance are like really important things that are happening in central cities, okay? And so these statistics are going to be useful for thinking about things like housing investment and housing maintenance. We know those are very important economic decisions. Those are important decisions that people make in their lives. And we also think that these housing decisions are important for neighborhood outcomes, so neighborhood sorting and neighborhood dynamics. And I would describe the evidence base on that as relatively thin. And so I'm really excited for the potential of these data to help us understand this period of central city decline in the middle 20th century and the important role that housing decisions may have played in those dynamics. Okay. As I alluded to, these statistics are presented at a high level of spatial detail. Typically in a central city, this is going to be literally a city block. And so this is a very rough guesstimate. You can think of the spatial unit here as having a population of about 50 compared with about 4,000 for a typical US Census tract. As Katie alluded to in her presentation, these are going to be the most granular statistics that we are going to be able to recover for some of these years, because the housing data was on the reverse side, and they weren't captured before they were thrown out. Okay, so I'm going to talk in the next couple slides about what in particular this sort of granular detail is useful for. But to sum up, this sort of high level spatial detail is going to be useful for studying policies and processes that occur at extremely localized spatial scales. Okay. Finally, what is the coverage? So this is going to be a large and expanding section of cities over time in the original block statistics. So the coverage in 1940 is 191 cities. Over time, they gradually add more cities. Finally, in 1970, the coverage of the block statistics is all urbanized areas in the United States. Okay. And so I think the real potential here is in the potential panel structure of the data. So you can observe a lot of neighborhoods and a lot of cities over many years, over many decades. That said, you can also go in depth into like one city's history. Okay. All right. Let me talk about two use cases that I think are potentially interesting, and focusing in on this sort of like very detailed spatial scale of the block statistics. So the first sort of typology here that I think the block statistics are useful for is to study like social processes that happen at extremely localized scales. And so one example of a localized process is residential racial segregation. And so this is an example drawn from South Philadelphia. And we're observing two census tracts in 1970 in South Philadelphia that have been highlighted here. The one on the upper left has a black share in 1970 of 28%. The one on the lower right has a black share of 16%. Both of these tracts are, like around sort of like the citywide average black share, right? And so looking at the tract data, you might infer, especially for this sort of tract on the lower right, like, oh, maybe this is an integrated tract, right? But part of what's going on here is the coarse granularity of the tract data is obscuring what actually is like a fairly segregated pattern, right? And so if we look at the block data, you see like a remarkable degree of residential racial segregation at the block level that's being obscured by the coarseness of the tract data, okay? And so that's one type of thing that block data are useful for, is to study these social processes that we think are happening at very detailed scales, right? That are smaller than the census tracts. Okay. A second typology of what these data might be useful for is to study localized policies. Okay. So this is an example that's drawn from a current project that I have with Jeff Brinkman and Kyle Mangum. Are they here? Okay, then I can say anything I want about this project. So this is a project about the role of expectations in neighborhood development and neighborhood dynamics. And we're studying the impact of proposed highway routes in central US cities. One of the analyses that we have in our paper is a matched runner-up design. And so the causal inference issue that we're trying to address is that if you want to estimate the effects of a proposed highway line, a proposed highway route, you need to have a counterfactual. What would have happened to the neighborhoods along that proposed highway route, but for the plan itself, right? And so that's a very difficult problem. It's a classic causal inference problem. One design that we have in the paper is this matched runner-up design. And so this takes place in the context of Philadelphia. And we're examining the Crosstown Expressway plans in South Philadelphia. The Crosstown Expressway was planned for South Street. So that's the upper red line alignment that you see in this map. What the matched runner-up design does is we identify in the historical record a lot of planning in the early 1910s and 1920s for a potential alternative route for the Crosstown Expressway. That alternative was Washington Avenue, which is this other red line on this graph. Now you can see the problem with tracks immediately, which is that these tracks are big relative to the contrast between Washington Avenue and South Street. At least two tracks intersect or border on both alignments. And so this just like, and then the other feature is there's just not a lot of tracks, right? And so we're gonna have problems implementing a runner-up design with the track data. In contrast, blocks are very small, they're granular. We have blocks that are very tightly aligned with the routing of Washington Avenue and South Street, respectively. And that's what enables us to estimate like an event study or a difference in design. Okay. What are our goals with this project? So those are two examples, localized processes and localized policies. What are our goals with this project? Okay, so what we intend to do is to develop and release block data for 16 cities for 4 census years between 1940 and 1970. We also want to release training and validation data that we're using to develop the models to digitize these statistics. And we also want to publicly release the code and methods that we're developing for this project so that future researchers can not only use the data that we're generating in perhaps ways that we're not anticipating, but also that they can apply these methods to any of the other cities that are in the block statistics, and you can source those images from libraries or whatever. Okay. All right. So in the remainder of the talk, I'm going to talk about the three kind of tasks in the pipeline, three problems that we have to solve. Those are shapes, situations, and statistics. Situations means like geographic location, but I worked hard to get the S's. And like throughout, we're going to be talking about kind of like the challenges that we've faced, and then kind of our current strategies. And I'm going to tag team this. I'm going to talk about the first two, and then Dan is going to take over for the statistics. Okay. All right. So shapes, situations, and statistics, those are the puzzle pieces that we have to fit together. So the first problem here is segmenting the block shapes from the maps. Okay. So this is a typical map from the 1940 Census of Housing Block Statistics. What are some features that I'll point out here? So the dark outlines here are tract boundaries. The bubbled letters that are kind of have this speckle pattern in, these are tract identifiers. Okay. These small polygons are blocks. These are the shapes that we are interested in. And then each block is labeled with a number in the interior of the block. Okay. So ideally, what will we do? Well, we identify all the polygons or closed loops. We'd vectorize them. They're blocks. We're done, right? That would be fantastic. Unfortunately, this doesn't work. So these are true positives. Yes, we could correctly identify some blocks. On the other hand, there's some false positives here, right? And so these like inner loops inside of numbers. This street name is a little bit too close to this line. And then the major problem here is these tract identifiers, right? And so, I don't know, I'll show you some more on the next slide, okay? So, for like the zeros and the street names, those are not really that much of a nuisance. We can just kind of throw those out because they're way too small to be plausible blocks. On the other hand, this is like a plausible block shape. And this is kind of like something that doesn't look like a block shape, but is in fact a block, right? So we have a lot of these sort of edge cases that we need to do. And so the tract identifiers are kind of a key problem. And with the 40 and 50 maps, you can kind of see they're just grayscale, and there's not a lot to distinguish between the shape of a tract identifier and the shape of a block. Okay. So what doesn't work? So templating doesn't work. So one thing you could do is you look for shapes that look like this. Unfortunately, the performance is poor. We've got to accept a lot of false positives. That's no good. What else doesn't work? Well, you might notice that there's like speckling in here. That also doesn't work because they're sort of inconsistent. These are like hand inked. So it's really kind of a nightmare. Okay, so what is our current strategy? So we are developing a neural network model. It's going to be more flexible than we can. It can learn more patterns that we can't really recognize, and it's going to help us to, I think that's one of the key features. The key virtues here. And then of course, it's also more holistic, right? Because we're going to be able to teach the model, not only like what is a block shape, but also what are tract identifiers and so on and so forth, okay? So let me just show you some of the preliminary results that we've had so far. So one of the problems here is how do you create training data? We don't have existing block shape files. So the solution that we've had some success with here is in simulating training data. And so this gets around the problem of hand annotations being relatively expensive. So what we've done is basically simulate 1940 census block maps by taking 1990 shapes and sampling these like tract identifiers and block identifiers and generating these maps. Because we've simulated them, we know exactly pixel by pixel what's on the training mask. Okay. Of course, this is training data. The question is like, can a model that's being trained on simulated data actually do well on segmenting a real map? And the answer is like, so far, pretty good. And so this is a real map on the left. And then this is a pixel by pixel classification that's coming out of the trained CNN. And you can see it's doing a pretty good job of ignoring the nuisance features that we don't want, like these big tract identifiers. And it's doing a pretty good job of picking up the actual block boundaries that we need. Okay, and so then once we're here, it becomes pretty easy to vectorize this and turn this into a shapefile. Here's another example.
Were the railroads real line? Those real delineations?
Can you?
Yeah, they were. One there. They split. Yeah, but they did. Okay.
Yeah. Okay. Thanks. What's next? Better simulated maps, some hand annotations. The model currently is a little bit too aggressive in removing tract identifiers. So we're talking about maybe a Gen AI thing where we're going to inpaint some of the missing lines. And of course, we're like very open to suggestions about how to improve this. Okay, that was like 40 and 50 and a little bit of 60. 1970 is like completely different. And so that we have like a whole different kind of, we have to do a whole different kind of model for 1970. Okay. Problem number 2, georeferencing, okay? So the traditional method of georeferencing, people here will be familiar with, is we have a scanned map, and then we have a reference map with a known geography. And the traditional method is you find a point in the scan map, a red star, and you find the corresponding point in the real geography, this red star, and you just click, okay? And so now the software knows that these 2 points should be in the same space. If you get 3, then you for an image, then you can perform an affine transformation and put these maps together, right? So this is the manifolds mapping that Vitaly was talking about earlier today. Okay, what are the disadvantages? This is like incredibly labor intensive. 3 points is necessary, but it's often not sufficient, especially with these like hand-drawn maps in the 1940s. They're not really to like a correct scaling. And so you get like, all of these like errors, right? So there's these small like georeferencing errors. So we want to get faster at this. We have like, like thousands, tens of thousands of maps to process. How can we get a computer to do this for us? So we're going to develop this algorithm that's based on something we can segment easily from the scan maps, which is the tract boundaries. Okay, so from the from the scan maps, we can segment the tract boundaries. The tract shapefiles already exist, right? So we can just download those from NHGIS. And now the problem is a little bit simpler. We just have to match up this shape to that shape. How hard could this be? Well, it turns out kind of hard. The computer doesn't know that this point and that point are the same. It can generate a bunch of candidate links between the 2 sources here. But now the problem is like, well, how does the computer learn like what are the correct links to do the georeferencing? And so the algorithm, which is like a ransack-based algorithm, is basically as follows. So out of these, candidate links, the computer is going to make a guess, use a small share of the candidate links. It's going to perform the transformation. Then it's going to evaluate the guess. For the selected links from the first step, how much do the maps overlap? And we're going to repeat this over and over and over again. And the thing is, we only have to get it right once, right? And so let me show you an example. So this is, try number 1, not so great. Try number 2, wonderful. Try number 3, bad. Try number 4, bad. We got it once. And so that's the one that we're going to keep, right? Okay. And that's the resulting georeference. Okay. So that was shapes and situations. Dan's going to talk about statistics. Oh, okay.
Which I don't know which direction is. Okay. All right. So I won't go over this again, other than to say that for the statistics, the problem is a little simpler in that 1970 already exists digitally. But the scale of this problem is that there's about 2,000 pages of tabular data per decade, or about 2.5 million cells of data. And what we want to get is the data in structured tabular form, with the rows and columns properly associated, and with accuracy better than 99%. So I'll skip right to the bottom line about the method we use, which is, in concept similar to what Vitali described. Basically want to isolate the components of the table as much as possible, getting down to the column level. We do first pass with Tesseract, then we create an algorithm to structure the table, and then build a second stage ML model after we pass it through Tesseract to correct errors. So we lean on an existing model, and then we can improve a lot from there. And we get pretty great results, which I'll talk about in a second. But this approach really only makes sense if your data set is large and consistent. As Vitali described, there's quite a bit of iteration and tweaking to get something that works. It scales really well once it's there, but it's not easy to get there. So our custom solution here has an error rate of 0.07%. And that actually is better than humans. Human data entry had an error rate of about 0.12%. Actually, a lot of that error, something like 3/4 of it, came from the table structuring problem. It's actually similar to what Vitali was saying, where that actually is one of the harder tasks. It's very hard to keep aligned when there's missing cells and the scan is all warped. And that's where our model here can beat human entry. And how does that compare to some out of the box? The thing that I found worked best for this problem was Tesseract. However, this also gets quite a big assist from the table structure. Tesseract is pretty useless for structuring the table. And we get a 13% error rate there. So our model is about 200 times better than Tesseract by itself. So why not use the out-of-the-box solutions? So the first thing that, it's kind of classic example is to use Adobe. And this is a really simplified version of the table. I've just kept 2 columns. And it does okay on the OCR task. I don't exactly quantify it here, but you can scan through here and say, we're in the 1 in 10 error rate or something like that. However, it's absolute garbage for the table structure. You can see here that there's not a value for the price of dwellings for every row. And Adobe just collapses that all into one row, and it doesn't give you in a format. You can't get the data out of Adobe in a format that you can fix that. Okay, so another thing that a lot of people use is Textract. So here we can get to a more complicated problem. And with Textract, when it works, it really works. So for this table, which I've cherry-picked to be a positive example, it has a 1.5% error rate. And if you ignore little table structuring errors, and you're just thinking about the text recognition task, it's got a 0.22% error rate. And the algorithm that I use to structure the data, you could use on Textract equally well. So you can really think about it as that 0.22%. However, when Textract doesn't work, it doesn't work. And to the human eye, this table looks exactly the same in structure and font and all those things. And there's not an easy way that I found to get Textract to behave well on this table. Cropping in and out, changing, blurring, changing font size, trying to remove noise. You can get it to behave better, but there's not like a consistent way to do that.
What triggers that difference?
What
triggers that difference?
I don't know. I think that primarily what's happening is that this stuff here, it's reading these as like one character. So it's picking the wrong orientation for the page. But I haven't been able to determine, what is the reason why this happens. Okay, and that will be actually okay, again, if that was just a page or two that happens. But for Philadelphia, there's 169 pages, and Textract fails in a useless manner 51 times out of 169. So it has a page level error rate of 30%. So while we can fix these little errors that happen when it works, we can't really do anything consistent about the catastrophic errors. And that's why we go through the effort of building a custom method here. So I went over this before, so I'll be brief here, but the idea is to drill down into individual components of the table as much as possible. Let's get just the table and then each individual column, and then we can pass that through Tesseract, and I'll argue about why I think Tesseract is actually really good for this application. And then we need to structure that back into a table. And once we have it structured back into the table, we can match it to labeled data. And that's where we can train a model to really get very good results. It's also key throughout, as with the LLM example, to be like constantly visualizing and correcting what you're doing. As you're doing it, it's really easy to fix if there's any small errors or tweaking you need to do. You try to come back to it later, the task becomes much harder. And we want to make those steps and build little tools to help us throughout to make it as easy as possible to do these somewhat manual things. And then, of course, we can also do a final check versus the track figures that already exist. Although I've discovered in this process, which shouldn't be surprising, is actually quite a lot of errors in the tracked transcription as well. Okay, so I'll show you some visuals of what I mean by this stuff. So the first thing we want to do is isolate the table body. So to do that, we can just pass it through Textract once, and the results from there tend to be good enough. And you can chop the table up into components and make the image smaller if this doesn't work the first time, that we can scan up and down the image. And we can just ask, where does the text go from mostly alpha to mostly numeric? And that lets us chop the header off basically 100% accurately. And then we can also, there's also a footer on this table with some notes about how these things were reported. You can chop that off pretty easily too. Okay, so now we have just the table isolated, and we can straighten the table out such that this core part of the table here, the table body that we care about, is as straight as possible. And we can do that pretty simply as well. We can just draw a rotated bounding box, determine its rotation relative to the center of that box, and then straighten it out. I should have chosen an example here where there was more straightening, but sometimes there's a few degrees of rotation here, which makes a pretty big difference in performance. Okay, and then the other thing here is to ABC. Always be checking. We want to make quick visuals throughout. We can throw this into a PDF, and you can scan through, and you can see if there are any tables that I messed up. Do I need to tweak any of the parameters I've used either in the models or the rules that we're using throughout here? And I won't show you these types of visuals again, but basically for every key step in the pipeline, there's a quick visual that you can have so that you can look through it. Okay, isolate the columns. So in order to do that, we aggressively look for anything that could be text. And we can do that basically in two stages. We can pass it through OCR and keep anything that's a character. And then we can also use like CB2 contours and find anything that's a contour that's approximately the same size as the font on the page. And then all we have to do is we can delete those, and we smear what's left a little bit horizontally and aggressively vertically. That'll close. It's a little hard to see in this image, but there's like little gaps in these lines, so that these column separators are not like, especially here you can see there's gaps here. So we need to smear that, and that looks like this. And this is why it's also important to aggressively remove anything that could be text, because you can see even little small things from our aggressive vertical smearing get pretty long. Now you can see in this image, we basically got the columns. We just find the n-1 longest lines that are nearly vertical. And that's where n is the number of columns. All right, our columns are isolated. And now we can deal with each one of these. We can view each column as its own. Again, ABC, and visualize these to make sure that you haven't done anything bad. Okay, and this is where we can apply OCR. And so I found Tesseract is really useful here. Tesseract gets kind of a bad rap because out of the box, it almost never works well. But it's also highly sensitive to the input parameters and therefore highly flexible and governable. And something really important here for the results was to use a restricted character set and to have character level confidence. Some other tools let you restrict characters. Some of them give you at the character level the confidence. But the performance of a lot of the more modern models get much, much, much worse when you restrict the character set. While Tesseract, which is a little bit older, it's less sensitive to that and yet makes the task simpler from the correction standpoint that I'll get to next. And from that, we keep the character level text and the bounding boxes for each character. Okay, and then we need to structure that back into a table. And because the tables are consistent, we don't need to rely on a model. We can actually just use the internal consistency of the table. This can actually allow for a lot of warping inside of the table. Just start with a column that's always populated, and then look right and find the nearest two-way neighbor. So i.e. like each cell should be associated with a cell in the next column, and you want those angles to be similar across every cell, and you can allow for there being empty values. And that will also let us create a synthetic cell for cells that are empty, or maybe we didn't read any text in them, even though we should. So we won't mess up our table structure, even if we had an OCR error. And then we can repeat that same process, moving left and right to cover all the columns. And ABC, as always, with the visuals that looks like this, that lets you see how you've connected your row together. And the orange there shows you where you've created a synthetic cell, and the blue where the orange connects is like the point that represents that cell. And why go through all that? Well, it lets you do stuff like this. So this is the 1960s tend to be really warped. And most, or basically all other models that I've tried that were supposed to work out of the box, they view a table as something that has a uniform grid. And again, you can think about it as like much of the training data that's high quality training data does have a uniform grid. So that's a reasonable thing for them to assume. But the reality is that a lot of data doesn't have that format. If you just drew a straight line here, you would actually end up associating that row with three different rows. And with this algorithm here, you can get quite a lot of curve and correctly associate that stuff. And this is, again, where the process is able to beat the humans. Okay. And now the last step is pretty simple, because we have the character level information. We've structured that into a table. We can match it to labeled data. And we actually got really lucky here. We didn't have to go and get our own labeled data. The Mapping Segregation Project in Washington, D.C., they hand entered all the data for 40, 50, and 60 for D.C. So we can apply all these earlier steps to D.C., and then we can train a model based on all this information to get better than out-of-the-box OCR. And the model is really simple. We're predicting multi-class character on the left, and then we're taking the pixel value by position in the bounding box, what Tesseract predicted, and Tesseract's confidence in that prediction. And then we do all the normal ML stuff. We grid search with cross-validation to tune the hyperparameters, and we apply the model out of sample to all the remaining cities. And that's the performance statistics that I gave in the beginning. It doesn't have anything about Washington, D.C. in there. Okay. And then the last thing we can do is we can use the internal structure of the table to correct things. Owner occupied less renter occupied should equal occupied. We can check for outliers at the column level, and we compare the stats to the track level totals, being careful to account for suppression. So there's certain things where the numbers aren't going to add up, but you need to make sure they only add up within the boundaries of what you expect for suppression. And then I think another key thing is to make any corrections that you're doing easy. So we built a little Excel tool, basically, that is generated with Python. You can just grab the image that the character or cell that you're trying to correct, what your guess is, and then a human can go through pretty easily and correct those. And I will admit that I've cheated for the tracks, and they're all done this way because the tracks are very hard to get accurate because they're not consistent across cities. And they tend to be like right in the center of the book, and therefore extra distorted and black or overexposed. So caveats. The approach requires customization per data set. I can't use the model that I use for 50 to get something accurate for 60 and 40. And there are manual steps that remain. Identifying which scans are usable, finding the page ranges in the source documents. It's actually a lot of the documents for 50. There's missing pages. So you have to go get them from somewhere else, from some other scan. They'll be there all the way up to page 100. Then there'll be 4 missing pages, and they'll be all there again. So there's going to be manual to check there. And it's also important to be doing this, the ABC. It's easy to introduce an error in your pipeline that then propagates. And it's very hard to catch if you haven't done that early on. And where are we? So I'm scaling up this to finish 1950. And I'm refining issues with the 60 and 40 models. And then I'm interested also in seeing if I can get a little bit better with the track identifier, stop the cheating there, and also, inspired by Vitali's work, where can I use in Claude or maybe other LLM-based service for first cut, either to help with probably mostly to help with the track identifier, since with all the other stuff is working pretty well. So overall in this project, we're targeting to get the census of housing block statistics from 40 to 70. And we're going to develop and release this data for 16 cities, including the training and validation data that we have, and the methods and code. We're also going to include we're working on getting a bunch of labeled data for the maps as well. So we'll have a truth set for that, not just the results. And that's broken this down into getting the shapes, the situations, and the block statistics. And of course, questions and comments are welcome.